Okay, thanks. Thanks for the opportunity to talk about PICO. PICO is the probe of inflation and cosmic origins. It is one of 10 $1 billion scale missions competitively selected by NASA in 2017 for an 18 months mission study, and it is now under consideration by the decadal panel. First, I want to thank many members in this workshop and otherwise in the community for supporting the PICO study. We had in total 213 authors and endorsers. PICO is a millimeter, sub-millimeter polarimetric survey of the entire sky. It will produce the deepest maps ever made of Stokes IQ and U parameters in 21 frequency bands between 20 and 800 gigahertz. The maps will have resolution between 38 and 1 arc minute. The 8 maps at frequencies above 200 gigahertz will be the highest resolution full sky maps ever made. Each of these maps will be constructed from 10 independent, redundant, full sky surveys, giving stringent control of systematic uncertainty. PICO will use 13,000 bolometric transition net sensors and will make a 5-year survey from L2. Please note that number, 13,000, when you consider later on the sensitivity of the mission. Only 13,000. With these specifications, we accept noise baseline of 3,300 Planck missions, and our best estimate is that it will actually perform as 6,400 Planck missions. PICO has 7 primary science objectives, but as shown in this slide, it will have much broader impact. Today, I will only talk about a subset of PICO's future impact. The talk will be fairly high level, and then later on, Mathieu will talk about foregrounds. I encourage you to go to the website and to check the archive for the full study report and the decadal project white paper. PICO's first science objective is to constrain the tensor to scalar ratio R. Textbook inflation models, where's my cursor? Here we go. Textbook inflation models that naturally explain the observed spectral index and have super Planckian masses as the dominant scale in the infotone potential have R larger than 5 × 10⁻⁴. PICO requirement is to achieve an upper limit of less than 2 × 10⁻⁴ at 95%, or a detection of 5 × 10⁻⁴ at 5 sigma. The family of Planckian and super Planckian models are shown here in dashed lines from 4 Planck masses to 1 1/2 Planck mass. PICO is the only next decade instrument that can reject in high confidence a Planckian or super Planckian mass scale in the potential. You may ask, why is it important to achieve this rejection of Planckian mass scale in the potential? The community white paper discussing target R constraints in the next decade identifies only one threshold below 10⁻². It is the threshold associated with rejection of Planckian mass scale in the potential. And the paper says, if this threshold is passed without detection, most textbook models of inflation will be ruled out, and the data would force a significant change in our understanding of the primordial universe. As you can see, PICO only PICO can reach this threshold with high confidence. If the universe is such, though, that R is at a level of 10⁻�3, PICO has the highest signal-to-noise ratio, most stable thermal platform, and the simplest design to shield against systematic uncertainty. It is the only experiment with a signal-to-noise ratio, sky coverage, and multiplicity of bands to give high significant detections in several separate independent patches of the sky. But can the foregrounds be handled at these low R levels? A Fisher forecast that includes correlated foregrounds, 40% sky coverage, and delensing gives sigma R of 2 × 10⁻⁵, which is 5 times lower than our 1 sigma requirement of 1 × 10⁻⁴. We set the more stringent requirement based on map level simulations. The map simulations have various PISM and other input foregrounds and various other parameters. The reconstruction of the CMB using GNILC, as you know, a non-parametric approach, shown here for one foreground model, correctly reconstruct the CMB in this case, the 15% lensing B mode, over all angular scales, except for a factor of 2 bias at the lowest L's. At these low L's, the signal for R 5 × 10⁻⁴ is a factor of 10 higher. At L equals 100, the residual foreground contamination shown in yellow is a factor of 4 lower than the expected signal. But it might even be lower if we were to run the foreground cleaning only on a smaller, cleaner patches of the sky. These results are approximately reproduced when we change the assumptions of what the foregrounds might actually be, as we show here, and I point you to Mathieu's part, which will come a little bit later, talking more about foregrounds. No other experiment has yet shown similar level of foreground separation. PICO's third science objective is to give at least a 4 sigma detection of the neutrino mass. Only cosmology can give the absolute mass scale if it is near the minimum allowed. The constraint comes from the effect of neutrinos on the growth of structure, which for the CMB is revealed through the lensing maps. Oops. Determining the some neutrino mass requires 3 ingredients: the matter density, the growth of structure, and the optical depth ionization. The matter density will come from baryonic acoustic oscillations from Desi and Euclid. Growth of structure will come from PICO's own high signal to noise ratio lensing maps. PICO's map will be 10 times deeper than Planck, and compared to any other of the decade's forthcoming instruments, it will have the highest signal to noise ratio on the power spectrum of the lensing potential, all the way to L equals 1000. The optical depth ionization will come from PICO's own tau measurement. With these data, PICO will give a constraint of 14 millielectron volts, a 4 sigma detection of the some neutrino mass if it is the lowest available. It will give a 5 sigma determination or higher if the mass is about 70 millielectron volts. The lensing data will be only one of 3 independent ways, or 3 different ways, that PICO will constrain the neutrino mass, all at approximately the same level. Only PICO can provide 2 of the 3 inputs, the growth of structure and optical depth ionization, within a single self-consistent, self-calibrated data set. No other constraint in the next decade is expected to be tighter than PICO's. Light species beyond the 3 known neutrinos could have existed in the early universe and fallen out of thermal equilibrium. CMB spectra are sensitive to the number of light species, as everyone knows. Only 3 neutrinos gives an effective 3.046, which is consistent with Planck. PICO will improve upon the constraints by a factor of 6, probing thermal equilibrium temperature for spin-modern particle that is a factor of 300 tighter than possible today. With N effective as well, no other constraints in the next decade or beyond is expected to be tighter than PICO's. Milky Way stars form at much lower rate than would be expected purely from gravitational collapse. The prevailing thought is the turbulence and magnetic fields slow the collapse. But what are the quantitative details? What is the average ratio of energy stored in the magnetic field to that stored in turbulent motion? And what is this ratio over spatial scales from the diffuse interstellar medium to dense cores? To make progress, we need measurements of magnetic fields over 4 orders of magnitude in spatial scale, from the entire galaxy down to the scale of dense cores. PICO will make 86 million independent B field measurements, a factor of 1,000 more than Planck. The image here on the left shows in yellow the sky area over which Planck had polarization fraction measurement errors of less than 0.7% with 5 arc-minute resolution. In green, we show the area over which PICO will have the same errors with 5 times better resolution of 1 arc-minute. It is the accuracy in the polarization fraction measurements that give the information on the orientation of the magnetic fields. The data will also give magnetic field maps in 70 external galaxies. Currently, only 2 are mapped. And it will map 10 Milky Way clouds with 0.1 parsec resolution giving for the first time a connection between the magnetic fields in star-forming region and fields in the diffused ISM. PICO will bridge the gap in the measurements between the largest spatial scales and the high-resolution data of SOFIA and ground-based instruments. Only PICO can generate such a data set. PICO's full sky coverage will generate legacy surveys and catalogs that will be used for many years. It will be used to understand early galaxy formation and dark matter substructures from 4,500 strongly lensed galaxies at Z up to 5. That's a factor of 400 more than today. Information on early cluster formation from 50,000 protoclusters at Z up to 4.5. That's a factor of 1,000 more than today. It will give correlation of dust with galaxy properties coming from 30,000 galactic dust SEDs, factor of 10 more today. And it will give information of physics of jets and order of magnetic fields in external galaxies. Just like WMAP and Planck set the cosmological paradigm for the 2010s and 2020s, PICO will set the cosmological paradigms for the 2030s. Here I'm showing the increase in precision of cosmological parameters over the years, starting from COBE and going forward. The vertical axis is a standard figure of merit used also with other surveys to quantify the volume of uncertainty in parameter space. The larger the value, the smaller the uncertainty. For the base lambda CDM 6 parameter model, Planck had improved upon WMAP by a factor of 300. In the same figure of merit units and on the same model, PICO will improve by a factor of 50,000. On an 11 parameter set showing in the upper curve, including R and some neutrino mass and effective and other parameters, PICO will improve upon Planck by a factor of 120 million and will almost match an essentially cosmic variance limited measurements. PICO will set the cosmological paradigm for the 2030s by either validating lambda CDM or sweeping it aside for another model. The PICO implementation builds upon experience with Planck and other current CMB missions. It is based on a 1.4 meter entrance aperture, 2-mirror telescope. The primary mirror is at ambient temperature. The aperture stop and a secondary mirror are actively cooled to 4 Kelvin, and the focal plane is maintained at 100 millikelvin with an adiabatic demagnetization refrigerator. Here we show the focal plane, the layout of the focal plane. The lower frequency bands have 3 color pixels and single colors at the high frequency bands. As I've said in the beginning, we have completed the report, submitted papers to the dedicated panel. It is being under reviewed by the dedicated panel. And for about the last year, we had a foreground working group meeting quantifying PICO's capability to achieve its requirements. And Mathieu's part, which is forthcoming in a second, will talk about this. So to address some of the requests that have come in from the Cosmoglobe group, why PICO, why now? Which goes to the question, what is unique? PICO has transformative science. Much of the science can only be done from space. Further progress of CMB requires a leap in sensitivity, foreground characterization, and systematic control, and space is best suited to provide this leap. PICO is the only instrument with a combination of sky coverage, resolution, frequency band, and sensitivity to achieve all of the science with one platform. Other planned efforts are equivalent in cost to PICO, but with more bands, higher sensitivity, I should say, over a larger range, not necessarily more bands, higher sensitivity, better control of systematic, and simpler instrument implementation. PICO is the most cost-effective path for progress. Other questions, data analysis challenges. The first thing I would say, the data analysis challenges are probably simpler than most other decades experiments. Only 13,000 detectors, all of them in the same receiver, at the same temperature, all calibrated together, absolutely and relatively the same way, and in a thermally stable environment. There's no modulation. The no modulation requires us to look more carefully into 1 over F noise. If questions arise, we have some preliminary results, but I didn't plan to show them today. We have a data volume of about 6.1 terabits per day, and we expect 340 terabytes for the entire mission. That's compressed. Systematics. The first thing I would say, it's probably the cleanest data set forthcoming for all the reasons I've already mentioned and that I mentioned here. We have already studied for the report gain variations and polarization angle calibration, and those results are shown here. The residual from gain calibration and for polarization angle misreconstruction at the level we expect are much smaller than the requirement. We do need to assess further far side lobes and the beam characterization. This has been mentioned also by Reho. There's a question about what are the data release products. It's too early to say, except to say that I think the entire PICO team is strongly supportive of the Cosmoglobe effort. And overall, the main challenges, I would say the combination of foreground and systematics to achieve are less than 2 times 10⁻⁴ at 95%. So now we migrate to the foreground separation update by Mathieu for the next few minutes. So the challenge is to demonstrate required upper limit on R equals 0 and recovery of R 10⁻³ with multiple possible foregrounds. I did talk about this a little bit. Mathieu will show more work. The methodology is to, as I mentioned earlier, to use several input skies, various different foreground skies, analyze them with parametric and non-parametric techniques. The parametric is led by Ragnhild Orlean and the Oslo group using Commander. And the non-parametric is led by Mathieu and Remazeilles at the moment using NILC. And the results today will only concentrate on the non-parametric by Mathieu. So at this point, I'm going to stop my sharing and Mathieu will continue the presentation.
All right, we can see your screen, Mathieu.
Can you hear me?
That's right.
Okay, great. So this follow-up activities on PICO Foregrounds is led by these few people which are listed here. As Shaul mentioned, we are analyzing several sky models, and we have to say that this PICO data challenge is an open data challenge with a free set of simulations. Simulation with 21 maps at each frequency with a specification of PICO, and everything is summarized on this web page, and the simulations are available at NILC. So we are considering a variety of realistic foreground skies. So they are listed with a certain terminology. I can explain what it is. So model 91 basically is a Planck state-of-the-art of the foreground sky, single modified blackbody for dust with beta and T variations, synchrotron power law with beta variations. Model 92 is this Finkbeiner Davis Schlegel model where you have 2 dust modified blackbody components in the sky with uniform beta 1, beta 2, but variation in T1, T2, synchrotron power law plus curvature, and also some polarization of AME. We have also more sophisticated or more complex model, like a model by Brandon Hensley on a physical dust model, which is not a modified blackbody. We have also model 96, which in which dust and synchrotron are consistently derived from MHD simulations, in which case you have also a multiple modified blackbody dust components along the line of sight. And model 98, which is from Martinez-Soulaesch model, which is a 3D dust model, so including some decorrelations and layers with different modified blackbody along the line of sight. So today I will show this result starting with these 2 kind of skies. And I will speak, as Shaul mentioned, about the non-parametric approach. So NILC, which is an internal linear combination in a needlet, which is a spherical wavelet space. This kind of method is non-parametric, which means blind to foregrounds or mute to foregrounds, I would say. You don't say any assumption about foregrounds. And in some sense, this kind of method is safe from mismodeling foregrounds. So showing result for first a fiducial value of 3 × 10⁻³ on the primordial signal in the sky. This is for model 91, Planck state of the art. This is one for 10 realization of CMB and noise. And what you can see on this plot, also in black, are the input CMB signal, which include some tensor or primordial signal at R 3 × 10⁻³ in dashed black. And solid black so include also the lensing signal. And so in light blue or cyan, you can see the recovered CMB after running the NILC component separations, the recovered CMB across the full multiple range. In green, you have the residual noise, which project into the recovered CMB B-mode map. And in red, the projected foregrounds or residual foreground contamination in your recovered CMB B-mode map. And so, and the gray band here just show theoretical signals that we expect in a range of R 5 × 10⁻⁴ up to 5 × 10⁻³. So as you can see, for all realizations, the signal is well recovered with a noise residual which is below the signal, and most importantly, the foreground residuals are have a power well controlled, much below 5 × 10⁻⁴. So this is the same plot, but average over all realizations. So the blue box here presents the recovered CMB with the error on the recovered spectrum, which include the cosmic variance from the primordial signal, from the lensing signal, and also sample variance from residual noise and residual foregrounds. And the important message here is that, as you can see, foreground residuals here in red are reduced at least 10 times lower than the primordial signal at 3 × 10⁻³. So these are quite spectacular results. And this is for model 91. For model 92, where you have 2 dust components in the sky, 2 modified black body, are these results. So again, foreground residuals are 10 times lower than R 3 × 10⁻³, even better for 92. I can explain why later if you want. And these are the recovered tensor to scalar ratio based on the recovered CMB B-mode per spectrum. So we have a robust recovery of the tensor scalar ratio with a 10 sigma detection of R 3 × 10⁻³ for both sky models. So it's quite, it is quite robust, whatever the sky model is. And now I will show you the result for R = 0, so no primordial signal in the sky, just a pure lensing signal. This is useful to understand what is a kind of upper limit we can achieve with PICO. So again, model 91, Planck state of the art of the foreground sky. So this is again for 10 realizations, this time without any primordial signal. So in blue, you see the recovered lensing signal, no bias, residual foregrounds and residual noise are below the signal. This is the same plot again, but average over all realizations. So you can see the angular power spectrum of the recovered NILC CMB B-mode map, which is shown by the blue boxes here. And the power of foreground residuals in the recovered CMB are much below, I mean, 3 times lower than R 5 × 10⁻⁴. Thanks to this large number of 21 frequency bands extending from 20 to 800 GHz, you can achieve such a very good result with a non-parametric method, being safe of incorrect foreground modeling. This is for model 92. Again, similar results with a very low foreground residuals on the recovered CMB mode power spectrum. And the recovered tensor scalar ratio. Here you can see for both model 91, 92, without including delancing or by doing 60% delancing, just to give you an idea. This is a kind of recovered tensor scalar ratio we have. For both model, R is consistent with 0, and sigma of R reach 10 to the minus 4 for both sky models. I will now discuss about the importance of high frequency channels of PICO. So I go back to this model 91 for the baseline PICO configurations, 21 frequency bands from 20 to 800 GHz. This is the results for the baseline PICO, which I showed before. And now I will show you if, the results if I discard the high frequency bands of PICO, stopping at 450 GHz, let's say. And you can see, if you can see, I'm switching between the slides. You can see how the residual foregrounds increases. The residual foreground power increases mostly at reionization scale at low L when I discard high frequency bands of PICO. And similar for model 92, this is a baseline result for the full configuration of PICO. And now rejecting high frequency, without high frequencies, you lose in terms of foreground residuals. You can see now the impact on the recovered tensor scalar ratio. These are the baseline results for model 91, Planck state of the art on the left, 2 modified black body for dust on the right. This is the baseline result which I showed before. And now if I switch to the case where I discard high frequencies, you see how the likelihood of R shift towards the right, so increasing the bias on R, and so yielding a 1 sigma bias typically without high frequencies, and thus exceeding the required performance of PICO, which I remind should be 10 to the minus 4 for R equals 0, sigma R 10 to the minus 4. So you see here the impact. So to summarize, PICO allows to control foreground contaminations below R 5 10 to the minus 4. NILC results are quite robust irrespective of the foreground sky complexity. I have shown the importance of PICO's high frequencies to mitigate residual foreground contamination. There are forthcoming results from NILC on other foreground skies. Some of them were already in the report, but we are constantly updating with this follow-up activity. But NILC result will be shown on model 93, physical dust, MHD, and multi-layer dust models. The next step we want to discuss in this group, and these are ongoing activities, is try to demonstrate that high frequency are of major importance, not only to help foreground cleaning, as I have shown, but also to help you trust your detections, to inform on false detection of R. High frequency will allow you to break spectral degeneracy over different dust models, which you can have on more narrower frequency range of observations. High frequency will be like red flags to provide you chi-square evidence for incorrect dust models. So this is crucial. These high frequencies are crucial. We want also to see what is the importance of having low frequency. We already started also the same game by discarding low frequency instead of discarding high frequencies. And we want to answer this question: do we need higher resolution observation at low frequency compared to what exists today? Why I say that? Because non-Gaussian small-scale fluctuation of synchrotron when integrated over larger angular scale, over larger beams, can effectively distort the baseline ACD of synchrotron models, introducing higher order moments or effective curvature on the power law synchrotron. A general question we want to answer also is which between increased number of detectors or extended frequency coverage provides more leverage on B-mode reconstruction and foreground cleaning. And I will finish by saying that parametric results are forthcoming from Commander by Ragnhild and the Oslo team. So there will be more results soon. And I will now leave the conclusion to Shaul.
Well, I'll just leave this on the screen. The summary is further progress requires leaps in sensitivity, foreground characterization, and systematic control, as everyone knows. PICO is the only instrument, as I said, that can provide these leaps within one platform. And as you've seen, analysis of foreground removal efficacy is ongoing.